In today's lesson, we are still looking at the focus standard from grade 8, Expressions and Equations, number 3. Use scientific notation to estimate very large or very small quantities and to express how many times as much one is than the other. So our topic for today is still scientific notation, but today we're actually getting to scientific notation versus standard form. So up until now, we've kind of been building up the pieces to really be able to grasp scientific notation. So our essential question today is, how does magnitude help us with scientific notation in translating with standard form? Take a moment to copy down your header and set up your question column and your note column, and resume the video when you're ready to begin. So we're going to start today looking right at the proper notation for scientific notation. And as we've already mentioned in our focus standard, scientific notation is used to express very large or very small numbers. We've talked already about how we use a base 10 number system, which every power of 10 moves the decimal point either left or right, depending on if it's a negative or positive power. So here's our proper scientific notation. It's always written as the product of two factors. So the first, and we're representing that with the variable a, and a is the coefficient, and it must be written in the form where a is greater than or equal to 1, but less than 10. So it can't have a place value greater than 1. It can have as many decimals as needed, but it can only have a digit in the whole number ones place. It can't go past that. And then we multiply that by the power of 10. And up until now, we've been using powers of 10 to estimate quantities. Now we're going to be more specific. So this power of 10 that we use in scientific notation is always going to be 1 less than the magnitude would be. So let's go ahead and take a look at our first practice problem. In our first problem, as we go from standard form to scientific notation, we're looking at the number of cells, and it said that the number of cells in the human body is 37,200,000,000,000,000,000. So as you can see, this is a pretty large number, and we're probably getting pretty tired of writing a lot of zeros, so this is where scientific notation comes in handy. If we first estimate it by magnitude, it's going to make it a little bit easier. So what would you estimate 37,200,000,000,000 to be as its power of 10 magnitude? If you came up with 10 to the 14th, I would agree with you, because magnitude is really based on the number of place values. So we have 3, 6, 9, 12, 13, 14 place values, so the magnitude of the number of cells in the human body would be 10 to the 14th power. So to write that in scientific notation, we want to be a little more specific. So here's our number again, but we want to be more specific in actually using these digits, any digit that is not 0. So we have 372 here, and we need to write it as our first factor so that it has a decimal point where the first digit is greater than or equal to 1, but less than 10. And like I said, it can have as many decimal points as it needs to deal with any of these digits that aren't zeros. So to do so, I came up with 3 72/100ths. So really, I just put the decimal point right there. And now we're going to multiply it by a power of 10, but remember, it's 1 less than its magnitude because we already have one place value right here. And so 1 less than 10 to the 14th power would be 10 to the 13th. So 37,200,000,000,000 written in scientific notation is 3 72/100ths times 10 to the 13th. If you multiply this out, you're going to get your original number back. So this is our shorthand for writing this larger number. Let's take a look at another one. So it said the approximate diameter of a human red blood cell is about 0 and 75 millionths of a meter. Tiny. So again, to help us translate from the standard notation, we want to first, into scientific notation, we want to first estimate this as its magnitude. So we had to look for where could we put a 1, and we would have put it right here. So I would say that to estimate 0 and 75 millionths as a magnitude, it would be 10 to the negative 4. Fourth power, 10 to the negative 4th. So same rules apply. If we want to be more specific and write this in scientific notation, we have to take this decimal, and again I just wrote it down as its original, and a little bit more. So here it is as its original, 75 millionths, but A has to be greater than 1, greater or equal to 1, but less than 10. So we put that decimal right between that 7 and the 5. So now 7 and 5/10 is greater than 1, but less than 10. It has that digit in the ones place. And then we multiply it by a power of 10, which is 1 less than its magnitude. And 1 less than the power of 10 to the negative 4th would be 10 to the negative 5th. So 0 and 75 millionths, written in scientific notation, would be 7 and 5/10 times 10 to the negative 5th. Let's try a couple going the other way, where we go from scientific notation to expanding it out to standard notation. I've done a few here looking at different objects in our solar system, and so it says that the sun's core temperature is about 2 and 7/10 times 10 to the 7th power degrees Fahrenheit. So we want to take this value in scientific notation and expand it out. Well, that whole idea about place value comes in really handy, that powers of 10, every power of 10 moves the decimal point. And so if the decimal point is right here, and we have a power of 10, or here, we have a power of 10 of 7, then that means we need to move the decimal point from here 7 places to the right. And so 2 and 7/10 times 10 to the 7th power is going to be 27 million. Because there's now 1, 2, 3, 4, 5, 6, 7 places behind that 2. Let's try one last one. The mass of an average hydrogen atom is about 1 times 10 to the negative 12th of a meter. So go ahead and see if you can write that in from scientific notation into standard notation. Again, I've copied it down already in its scientific notation form. The power of the 10 is going to tell us how many decimal places we want to have, but notice now it's a negative power. So we don't want this number to get bigger, going into the millions or billions. We want it to go into the decimal place value. So from our decimal point here, behind the 1 to the right of the 1, we're going to actually move it left 12 places. And so we come up with the number of this, giving us 12 digits behind the decimal point. So that's going to go ahead and conclude our video for today on scientific notation and translating from scientific notation versus standard form and using a little bit of magnitude to help us along the way. Take a few minutes to make sure that your notes are complete, and if you get a few minutes, go ahead and write your summary.